All right, folks, we're going to get started here in just a minute. Hey, Gee. Hey, Gee. Where is Gee? It's on. It's recording.
Hello, everyone. Welcome. I invite you to take a seat, make yourself comfortable, and let's get this started. Do you control music? Do I? No, I don't. Jim? How do I can't see the cursor on the screen. I can't reduce the window for it. Yeah, but I can't pass to the other one. Oh, do I need to go here? Can I get to the next one?
Yeah, that's the next slide here. You gotta find the cursor up here.
Oh, the cursor's up. Okay. Oh, there you go. You got it. Okay, it's up and down. Okay, perfect.
Yeah. And then see if I can move this out of your way.
No, otherwise we just do it on the screen over there.
You can if you can find it. Yep.
Yeah, I think we can see it there. And let me see if I can. Do I have the hyperlink there? Perfect. Okay, cool. Who are you? We're all here already. We're all good. Okay. Hey, Oh, the mic is not working anymore. No, it's on. No?
I think I did it.
Oh, you did it? Yeah, it's not, there's no more mic here.
That's what
1, 2? No? 1, 2? Hello? No? That's the music. 1, 2. There you go. Yeah, thank you. So hi, everyone. I'm happy to have you here. I'm happy to see that we have several people in person in this room. Good to see that social distancing is still being respected to a certain extent, but I think that everyone is happy to see and touch other people and just shake hands. I think it's a feeling that we all have been missing for a while. I know I have, and I'm pretty happy to be here with you. Hi to everyone who's online also, who's following us. My name is Guy Le Breton. I'm French, if you didn't figure that one out. You can, yes, it's a Polish name. We can talk about that a little bit later. You can call me Guy, unless you expect me to speak to you or answer any questions you might have. I am with H&P. I'm their International Business Development Manager, but I'm also part of the IADD. I'm a member of the board for 2 years, and it's my privilege and duty to host some of these events on a regular basis, such as the one that we're going to have today on Wellbore accuracy placement. Just a quick talk about this. In the industry, I think it's something that we believe has been a little bit missed or not taken care of as much as we would like. We spend a lot of time planning wells. We spend a lot of energy drilling those wells, but I don't feel that we spend that much time understanding where that well is and make sure that it is where it's supposed to be. And we all assume they are, and we all know what the word assume means, and it's not good.
That's a French word too.
Yes, absolutely. It's the same, and it means the same thing in both. Yes. And so unless someone is going to go down there and see exactly where the well is, you know, we all think that it's there, but it has significant consequences on the production, consequences on what you could get out of that well for which you spent a lot of time and money to drill. But we have 3 fantastic speakers today here to present all this. And I'm not the only one that is going to be hosting this event. I'm having here Peter Cho, who is my co-worker at H&P. He will be helping me host this event and hopefully take over, you know, bigger responsibility within the IADD. We always look for more people to help and make sure that we can bring good presentations and good discussions to the industry and make it move forward like we've done for many, many years. So, hey, with no further ado, you didn't come here to listen to me, you came here to listen to our presenters. I will let Peter introduce each one of them and make a quick review of their bio before they come up here on the screen, on the podium and talk about it. Let's go quickly through the agenda. We have this little opening remarks that I'm doing right now. We'll have the first presentation by Nico Koska, then we'll have Tim Patton, and then Robert Wiley. We'll have lunch at 11:30 to 12:15, and then we'll have an open discussion session. We like to do that. We've done it several times. Of course, during the presentations, you will have the opportunity to ask any questions. There should be enough time at the end of each presentation for room for questions. This is the idea here. It's not just for people to present, but also to have this open discussion. So don't hesitate to ask those tough questions. I think that all the presenters here can handle it. They're all experts in their domain. So please, you know, you can try to tease them a little bit and pique their, you know, and see what they have and what they can do, or talk about their subject as subject matter experts. And then at the end, we'll have a discussion where we'll have all the speakers come up and maybe other people that want to come up to the panel and just have an open conversation of what we think we could do for the industry to improve wellbore quality, wellbore placement. That's it for me. Thank you again for being here. I'm very happy. If there's anything that I can do to help you or make this luncheon more or easier for you, let me know. I'll be here in the room with you, and I'll let Peter take over. Thank you.
Hey, thanks, Guy. Thanks everybody for coming this morning. Like Guy said, it is a serious investment of money and time to drill a well, and survey management, wellbore placement, making sure we have our well accurately placed right where we want it, can help us as an industry make a lot more oil from the well. So, whoa. Okay. But my first experience with wellbore placement accuracy and survey management, I knew that I'm a drilling engineer and I was a company man before that. I knew that we got the survey and then it went off to someplace else and then it came back and it was corrected, and I thought it had something to do with the phase of the moon, and I didn't really understand, and it was several years before I really knew what was happening in that process. And today, hopefully, our speakers can kind of shine a light on that for us. Okay, without further ado, I'll go ahead and introduce Mr. Nico Koska. He's a Helmerich & Pan employee. He's the Wellbore Positioning Manager based out of Denver in the Remote Ops Center. His experience in MWD survey management ranges from the interpretation of large-scale geomagnetic models to tweaking small misalignment terms. He is an active member in the industry. He is a member of the ISHWA and the SPE. He is a published author within SPE, and he has presented his work in front of the IADC, ISHWA, and IADD. He's also the assistant chair for the Denver SPE of the Community Outreach and Philanthropy sections. Nico, come on up.
I understand that Nico got a new haircut.
What do you guys think? Good.
I'm not seeing the mouse option here. The mouse.
So it's over there on the screen. See it over there?
Oh, okay, I got it. I see it. There we go.
All right, thanks, Peter.
You know, apples are for smart people.
All right, thank you, Peter. Thank you, Guy. Thank you, IDD, for hosting this. Also, thanks H&P for sponsoring it. Appreciate that. It's really good to be here in front of everybody. It's been a long time. I think we're all ready for it. So I appreciate everybody turning up. It's going to be great. So I'm Nico Koska, as he said. Today, we're going to focus on wellbore placement accuracy. I'll be focusing specifically on survey management, what it is, how we do it, why we should do it. So the first thing to sort of know about survey management is that it all ties back to knowing your wellbore, where it started, where it is, how it got there, right? Interestingly enough, pretty much everybody associated with this well throughout its life is going to have some relationship with that wellbore placement in some fashion, whether it is the drilling group that's taking those surveys or decided to take those surveys, whether it's running casing, installing pumps, on the completion side. I mean, explaining things like communication between wells, frac hits, this all sort of ties into wellbore placement and knowing it more accurately. And the name of the game here is to basically reduce that positional uncertainty so that we can make better decisions at the end of the day. Another thing about survey management is that it's becoming more and more commonplace. It's becoming a term that people are now a lot more familiar with, especially on US land. Other places like offshore, namely, they've been using survey management for quite some time. Some places just aren't exactly early adopters. They want to wait until something is tried and true. And now nobody really wants to fall behind. And the operators that are being successful seem to be using survey management more and more. And so this is something that is becoming more of a household name, so to speak, in the industry. What I want to focus on today is what it is. What is it really? When do we use it and how do we use it? Sometimes it might not be necessary, and other times it might be necessary to go the extra mile and do a little bit extra survey management. And finally, I really want to stress on how we can work together to sort of roll this out in a painless way, keep improving, keep that communication and education just to the level that we're comfortable with, kind of integrating this into our everyday operations. So the first thing I actually ask you all, why do we survey? Can anybody tell me why we survey? Yeah. Yes, thank you. That is exactly right. We want to know where we are, right? Whether we're surveying our property lines or we're taking MWD surveys, we want to know where we are. But sometimes it's not just good enough to know where we are. We need to survey accurately. And this might be we're infilling an existing pad. And in this case, we might be surveying or at least correcting surveys from old historical wells because we want to know where we can put our new wells. Some new drilling campaigns are just designed to have tight spacing. And that's really important to know where they are. And that ties into avoiding collisions, which I think should be pretty obvious why we want to avoid collisions most of the time. I used to make the joke last year that survey management can kind of help us socially distance our wells, and then also help us kind of avoid trespassing. And that's, you know, crossing lease lines, crossing hard lines. Knowing where our wellbore is more accurately can allow us to achieve these goals. When we're talking about production, sort of mentioned it earlier, it can help you stay on target, stay within your zone more efficiently and just more often. And finally, just wellbore quality ties into all of these things. You'll hear the word tortuosity be thrown around a lot, just kind of explaining these bumps that are probably not recorded within surveys. But knowing those can really help us make those decisions down the line. How are we going to run casing? How are we going to install these pumps? What kind of life expectancy do we expect out of those things? So the first thing we need to talk about is the magnetic field. So the Earth has a magnetic field, and MWD tools basically work like compasses. They align with the magnetic field, which runs north to south. Unfortunately, we don't just put compasses inside of our BHAs anymore, even though that basically used to be, you know, single shot surveys. Go down, take a picture of a compass, bring it back up, see which way that compass was pointing. We also can't put a GPS inside of our BHA, because I don't know about you guys, but my GPS doesn't even work in my parking garage at work, so let alone downhole. So the things to know about the magnetic field of the Earth is that it's always changing. And before I get berated by the geophysics team, let me explain what I mean. It changes because there's a main field. The main field is in the outer core of the Earth, and it's just a bunch of magnetic material that's all melted and is sloshing around, creating this magnetic shield, essentially, shielding us from cosmic rays and shielding us from the sun's radiation. And it also allows us to take MWD surveys, which is why I'm talking about it. And this changes over time, all the time. That magnetic north today won't be the same magnetic north tomorrow or in 10 years. And it's always just sort of drifting around. And in fact, it has switched completely. The north and south poles, millions and millions of years ago. Hopefully it doesn't do that anytime soon, because it'll be an issue for our infrastructure. But that's what I mean by when it changes with time. But it also changes with depending on where you are. And this is a different component of the magnetic field. This is the crustal field. And this has to do with local geology, things that are present in the crust of the Earth. And all this means is that right here in Houston, the magnetic field is different than that in Dallas or in Hawaii. It's just on my mind, but or in Denver, anywhere. It's just going to be a little bit different because of the composition of the geology. And so as you move around, it also changes. The third and probably most fun part of the magnetic field is called the disturbance field. And this is caused by emissions from the sun that get captured in our atmosphere, specifically the ionosphere. And it basically electrifies that part of the atmosphere, and it looks really pretty. It's the northern lights or the southern lights, depending on which hemisphere you're on. But it can cause these really crazy and unpredictable swings in the magnetic field's behavior. And so if you're drilling up in Alaska or Canada or some places in Australia, this can be really, really difficult because as an, as an MWD or a directional driller, you know, you take a survey and you're expecting one number and all of a sudden it just swings the complete opposite direction. And so there's even some times where there's some stop drilling conditions where you just have to wait it out, let the storm pass, and then resume when it's a little bit more calm. But overall, the whole point here is that measuring this field better means that we know north better. And if we know north better, we know which direction we're going better. And this helps us place our wellbore more accurately. At the end of the day, having better data means that we can make better decisions. All right, well, that's all good, but how do we model this? Well, there's different ways to model this. The three main ways start with public models. Public models use magnetic observatories, which are essentially these small shacks scattered around the Earth, around maybe a few thousand miles apart. And they're measuring that main field. So remember, that's the main field that's sloshing around, moving around from the outer core of the Earth. It's kind of changing all the time, but so it measures it on a global scale, but it's a pretty high level measurement. These public models are also updated once every 5 years typically. And why does that matter? Well, because if you anticipate something for 5 years in advance and something changes early on, well, you basically either have to totally redo your model or you have 3 or 4 years, whatever it may be, of incorrect data. And we call those unexpected behaviors geomagnetic jerks, not because they're really annoying to work with, but because they actually just jerk into a direction that you didn't expect. If you want to get to a more high definition model, we use satellites. And these satellites also circle the entire globe, so we still get a global model. But these not only capture the main field, but they capture a little bit of that crustal field. So we get a little bit higher definition. So that's in that second map of Texas. These high definition models not only capture that crustal field, but are also updated yearly, which keeps that geomagnetic jerk issue a little bit lower. Finally, if we really want to get more detail, we can use what's called in-field referencing, or IFR1. IFR1 uses planes, boats, wave gliders, drones, whatever you can kind of fly over smaller plots of land. And it might only be the size of a small county, but you get a really, really detailed view of what the main field is and the crustal field is. I'm not going to get into IFR2, but that is what would actually capture those solar variations as well. So the big thing to remember here is the frequency of update is very important and the resolution that you get is important. So even though you might have a smaller area of data, you're going to get a much better picture of what we're looking at and what to expect. So to go one step further, we can take direct observations to create these models as well. So this is extremely helpful for places where we either can't fly, things like planes, or usually what happens is that a company or somebody has an IFR coverage somewhere, but they didn't really anticipate drilling right outside of it, but now they don't have that high resolution data. And so what can happen is just sending people out to the field. We'll send this guy with a theodolite out there, just taking some measurements. And we can add that data to the main field data or high definition data. And we can create a model that's IFR or better in terms of the resolution. This can also be applied on top of IFR1 if IFR1 we really want to reduce that uncertainty even more. But I think the really big value is creating IFR in places where there hasn't been that data captured yet. This is pretty great because it saves money and it saves time. And as far as I've been in the industry, I can pretty much say those are the magic words that I hear every time. We need to go faster and we need to do that to save money. So what's next? I mean, finding the magnetic field and getting a good model of that is great. There's other things that we sort of need to consider. MWD tools are created by 6 sensors, 3 magnetometers, 3 accelerometers. Some of them measure gravity, the magnetometers measure the magnetic field. And just like any measurements, these are going to have some errors associated with them. Well, the very biggest one is going to be drill string interference. And drill string interference affects that magnetometer that's pointing forward. And this is because your BHA isn't made of plastic. There's some non-magnetic material there, but there's also a motor and there's also some drill collars and all sorts of things that are creating this magnetic field. And it's essentially just like holding a magnet to a compass. That compass is just going to align with that magnet. And now we don't know where north is anymore. So if we don't take this into account, we're going to be going the wrong way. What's important to know is that things like choosing a better magnetic model doesn't really require any more workflow. You basically just get that magnetic model and use it in your data. Something like correcting for sensor errors does require workflow change. And so this can be a little bit difficult for some people who just want to do the same thing over and over. But this requires some sort of analysis. In some cases, this requires, extra surveys in some places, namely drilling east-west lateral can be very difficult or impossible if the proper workflow is not taken into account. But wait, there's more. There's misalignments. So I like to say there's different flavors of misalignment. The most common flavor, vanilla, is going to be our sag error. So this is probably the most common error when we talk about misalignments, and it's sag. Usually I just explain this as a steel beam supported on two sides, and for lack of a better word, it just sags in between those beams. The issue comes up when the MWD tool is in part of that sagging area of the BHA, and now it's not representing where the bit is pointed. And so over time, we just have consistently incorrect inclinations over and over and over. And now we have a TVD error at the end of the well. So it just kind of accumulates throughout the well. Other flavors, so the sensor packages, and what I mean by this are as accelerometers and magnetometers, those three aren't aligned axially, so it might be twisted, for example. And then single sensors, so maybe just a single magnetometer within the tool can be at, I don't want to use the word non-orthogonal, but it's no longer at 90 degrees, so it's just not where it should be. Things like sag, we cannot see with downhole data. QC data is not going to show you anything because you're still measuring properties. We're just not measuring the bits behavior. Single sensor and sensor package misalignments can be seen, but you really need to know what to look for. So some of these are tool face dependent. Some of them have different behaviors that if somebody's not really looking out for it, which typically in the field they're not, they're just going to go unnoticed. And these can have some pretty serious ramifications on bottom hole location that'll just go totally unnoticed if they're not being looked for. Another one that's been quite popular, in the last few years, survey frequency, also called the Stockhausen effect or survey aliasing. And this is basically all relating to surveys being hopefully taken at 90 feet intervals. But what happens in between, right? We don't know. There's this assumption that we have that surveys between them are just perfectly circular arcs. I don't think anybody truly thinks that's the case though. There's some sliding and then rotating, or maybe there's some rotating and then sliding. Maybe there's a little bit of both. Maybe there's, the formation is dropping you. Maybe your motor has some sort of impact on your inclination, and we're just not capturing that because all we look at are surveys every 90 feet. But lucky for us, most of the time we have the data, just nobody wants to look at it. It is pretty ugly data, but we're in the data analysis group, right? So we should be fine handling that. So once we actually look at the data, we can see these trends and we can apply those trends to our wellbore trajectory and basically get a more accurate representation of where we are. So this really isn't anything new. The first paper from Bill Lesso and Ed Stockhausen was about 20 years old. And these are things that offshore drilling has been doing for quite some time, because if you have the data, you might as well use it. And I think they are more inclined to use a little bit more technology. But US land and other land drilling operations are starting to catch on. And I'm not sure, this might have something to do with LinkedIn just kind of blowing up with this. Oh, thanks. Could you tell? Excuse me.
It's so much drier down here than it is.
Yeah, that's why I'm sweating so much. So basically, just to quickly illustrate this, the assumption on the left is showing what we're saying happens with 90-foot surveying. We're using a minimum curvature to connect these data points, these surveys. In reality, and granted this is a large exaggeration, so I don't want to say that there's going to be rig-sized TVD displacements, but you might have these weird undulations that are not being taken into account. Those black surveys, those arrows, are all at the same angle, but everything that's happening in between them is different. But now an important thing to remember is that it's not just all algorithms. Algorithms are great. Believe me, I love them just as much as the next person. But it's important to sort of see the other side of things as well. We need to focus on our workflow. We need to all be working together. There needs to be this group mentality of having centralized data, data that we can get once and we don't have to ask for again. If we're running multiple services as a survey management company, it's important to not be just berating people with, oh, I need a well plan. Oh, I need the well plan again. And I need the BHA reports and so on and so forth. It's so important to sort of build that relationship, make things easy, just sort of streamline the entire process. And then when I say QCing data, typically when we say QCing data in survey management, we're thinking, what's the total magnetic field? What's the dip angle? What's our total gravity? You know, this typical QC data is great and that's very important. But on top of that, we need to make sure that all of the data we receive is also QC'd. I think we had one well that was supposed to be drilling in West Texas, and I think they added a 0 or their geodetics was wrong, something, and they ended up in Florida. And I think when you submit those surveys, that should raise some red flags. We drilled the fastest, longest well in the world, you know. So those things are just very important, and they're easy to sort of let slide by. Things like your floor height of your rig, like your RKB, your location, all of these things. They just need to be double checked and cross-referenced, and we just need to make sure they're correct. So there's more than just a data analysis side. It's also a document revision side. Now, finally, how to operate. As a third party, survey management companies have tricky relationships. And I say tricky because we have a lot of clients, whether direct or indirect. Sure, only one of those clients is signing the check, but we need to make sure that we're in good communication with all of the other people, whether it's well planners, directional drillers, the MWD companies, because we're relying on them for the data and we're relying on them to help us out to get everything. We don't want to be bothering operators too much. You know, the real best way that we found to operate is that we almost want to be behind the curtain. Kind of like how Peter was saying, you know, he took a survey and he sent it somewhere and then they sent it back and it was corrected. Nobody really knows what's going on. Honestly, that's kind of what we want, because we don't want everybody else to have to worry about it and say, are you sure about that drill string interference? Or are you sure about this? It's like, we've got it. We're just going to give you the data. You can take care of all the other things. Drilling engineers have a lot on their plates. Survey management companies just have surveys. That's all we're doing. That's all we're looking at day in, day out. And so it's really important in my mind is to kind of create this cohesiveness, keep that communication open. And I swore I wasn't going to use this word, but you know, that synergy between people. And frankly, above all, what I would say is the education is just so important. Things like this, just kind of creating this discourse, having conversations, making sure people actually understand what we do. Because as much as we want to work in the background, we don't want to be some black box that nobody understands. We want people to understand the concepts, trust the concepts, believe in them, basically. So what I always kind of like to call it is management by exception. We don't want to be hounding people and calling them at 3 a.m. and saying, hey, you got a, you know, 1/10 of a degree correction. Like, I don't care. Like, that's perfect. That's fine. But if there's something dangerous, like an HSE risk or just something that's really going to impact the well's life further down the road and cost a lot of money, those are the calls we have to make. But it's important to kind of have that distinction and create this escalation process that we can be confident in and that everybody that we work with can be very familiar with. And so always available, never overwhelming. Somebody can use that tagline. I worked hard on it. In conclusion, better data, better decisions. Papa John's. I'm sorry. Better data does mean better decisions. And algorithms can't create that data a lot of times. They can help us correct that data. They can help us prove that that data is correct. But having empirical, measurable data that we can actually just look at and put our hands on, figuratively, is just very important. We can trust algorithms, just don't rely on them. At the end of the day, communication is paramount. Just keeping it open line of contact between every single one of the customers, everybody who's involved in the process. Keeping that education, just like things like today or all of the other conferences. It's all about just kind of sharing this knowledge and hoping that there's some knowledge shared back, answering questions, and then maybe leaving with some better questions. And finally, that transparency. we want people to know what we do. We don't want to be mysterious. We want, if somebody has a question, we absolutely love that. You know, sometimes you have drilling engineers that are just extremely involved in the process and just want to know, how does this even happen? Well, we need to be able to answer those questions. We need to have people who are comfortable speaking to those people. And that's pretty much what survey management is just keeping that communication open so that everybody can be on the same page. So with that, let's make some hole, and I'll open it up for questions. Yes, sir.
Yeah, Kevin Clark was performance drilling technology. How do you guys keep track of your metadata, the PHAs, and you keep track of the information associated with the surveys? You know, the bottom holes and the that's from the record, which is stored so that somebody in the future can take a look at it.
Yeah, absolutely. That's a great question, because we have been in contact with a lot of companies and we asked them for survey data from even just a couple of years ago, and it's gone, right? So it is really important to keep files. And now with everything being digital, it's pretty easy just to have everything in one centralized area. And we rely on that so much. And I mean, we have data going back to when our survey management company first started back in 2014. And so far so good, we haven't run out of space. But we have all the BHAs, well plans, you know, AC reports, all things like that. And it's really important to also keep it very organized. And so that's something that we have people for. Specific Alex here, that's a big part of his job, actually.
Are you keeping track of, say, all of the EDR data associated with tool faces when they come up from the certain operations and whatnot?
So it depends on the services requested. Some services do require that. Things like those TVD corrections with the continuous inclination data, that's straight from the EDR. There are also ways to do that with tool faces. That's kind of a whole other discussion, but anytime we have that data, we save it, but that's not for every single project.
You know, I've monitored a lot of the time operations in the last few years, and I've used your services and other services as well when I'm monitoring them. And you know, it does a great job of going over and correcting the current magnetic field and the MSA and all the things that are done. The one thing that I noted that sometimes the surveys that were being sent out, they would be corrected and they'd be magnetically corrected, but the survey was obviously wacko. And the reason the survey is obviously wacko in general is because the survey is taken right in the middle where there's a turn. The turn is being executed by the motor. And my theory is, and analysis is the reason that happens in turns is basically the same reason you have SAT, where you have this bend in the orientation of the measurement tool has been deflected. When you go around a curve, ideally what you want to have mathematically is you want to have the angle and inclination at the tangent of that curve to reflect what the direction is. But what happens is it gets deflected a little bit. And I think that it would be possible to correct for that, but you need to know if you're whether or not you're taking your survey in the middle of one of those bends.
Yeah, so there is such a thing as horizontal sag as well. And so that's exactly something that could be related to what you're talking about when you are taking those sharp turns. There are also offset center corrections or errors. And this just has to do with potentially the measurement tool not being aligned with the actual axis of the borehole, which would kind of result in exactly what you're saying, right? And so the tool faces would be necessary. Typically what happens there and how we correct for it is essentially taking surveys in a straight hole section and taking rotational surveys at the exact same point and look at the coning effect of different inclinations at a single place. And that'll tell you the angle that's offset. And so that's a way to correct for that.
You can't always do that.
You can't, well, because it'll change with changing inclination. So if you're in the curve, that's a very difficult thing. You'd have to basically take rotating shots at that survey.
Or have tool faces and be able to have a model.
You could, yeah, and that is something that should be taken into account for things like automated directional drilling decision making and things like that. Tool faces, motor yields, all of those things are extremely important. So yes, if we were to have that data, we would be storing it and keeping it indefinitely.
I think it's something.
I agree. Thank you. Yes, sir.
One question related to, you mentioned the DHA and the interference that they can create. Is it something which you correct with a model, or is it something which you can adjust prior to running?
So both. Depending on what we're trying to correct for the BHA, we would either want to model it pre-run, or we could even give sort of advice on, say, hey, we want to adjust so that we minimize vibrations. We want to minimize so that we extend the life of this bit, for example. Those are things that you can model and then give suggestions based on the planned borehole path. Things like sag, typically you're basically just saying, well, this is what your sag is going to be. We'll run it. And those are all things that basically have to be modeled, because with downhole QC data, there's really nothing that can change it unless you have like a near bit sensor measuring inclination and then a further back sensor. But even that, you'd have to basically be inside of the bit. So.
Or the amount of compression.
Yeah, and so that's something that we have an entire drilling dynamics group that does exactly that. Yeah, and that's interesting, but a lot of them are much smarter than me, so I don't want to go too far out of there. Peter, yes.
How far does the main field in the north move every 5 years when it's updated? Like how many miles does it move?
Well, that depends. That's why we have to update it so much. It's pretty unpredictable. There are maps of basically where declination has been. And declination is just basically where your north is relative to the Earth's spin axis. And typically, in my mind, it kind of does this like figure 8 thing, and then sometimes kind of comes away, but I wouldn't say too many miles, but then occasionally it flipped entirely. So
like how many, like in a 2-mile lateral, how many feet can you correct for by, like, say, we had just our main field data versus your IFR, like how many feet off can you get in your wellbore at the end of a lateral, and how much better can we do?
So depending on where you are, declination can get, near 20 degrees. 20 degrees, I don't know what 10,000 times the sine of 20 degrees is, but it's a whole lot. It's hundreds and hundreds of feet. But that's going from not using a magnetic model basically at all to using IFR. Typically the difference between main field models and IFR is closer to about a degree, maybe half a degree. And it obviously totally depends on where you are on the Earth. But that can definitely make differences 100 feet, even more sometimes. And then it's also worth noting sometimes though that, if you cross right on that line, they can be exactly equal. And even though you're using a less incorrect or a more incorrect field, you can get the same data, right? A broken clock is right twice a day, like they say. So sometimes that happens.
So it's very, very important to have sort of survey management to prevent, like, to address anti-collision, and then if you want to like maximize your pad, using survey management.
Well, another big thing is that it just gives more confidence. So if you're familiar with the areas of ellipse, the ellipses of uncertainty, even if you just reduce the ellipse and you're still smack dab in the middle of it, that at least gives you more confidence. And now you can drill with, higher separation factors. You're not just, always setting off the collision risk flags. You can actually drill the campaign that you might have been planning.
Thank you, Nico.
You're welcome, Peter.
Well planning is concerned, are you doing a lot of comparison between like the correct surveys on the
So it's, I mean, we'll always consult basically with the well planner if they need to make any changes after we correct. A lot of times what will happen is actually our services are more to correct after the fact in the vertical section because displacement is typically pretty minimal. And then do real-time corrections for every single survey throughout the curve and lateral. But sometimes the well planner will have to go and edit some things just based on that vertical portion not being exactly where they planned it to be. As far as torque and drag and drilling dynamics is concerned, that's something else that our the actual drilling dynamics team takes care of. So I can definitely put you in contact with people that would be more comfortable saying that, but. Right, I mean, you want to use, if you, that kind of ties back into the better data, better decisions. If you have better data, you're gonna be able to see more accurately what we anticipate happening. Am I getting kicked off?
And I could cut questions too short, but we will have an opportunity for the whole panel to answer questions kind of during the end of lunchtime. So let's try to stay on schedule. Our next speaker was supposed to be Mr. Tim Patton. He is, he had something come up today. So we will be followed by David Gutierrez from Superior QC. So David, come on up and. Got it.
All right, good morning. I am not Tim Payton. He had something come up, but I'll do my best to fill in. So I'm David Gutierrez, I'm Technical Advisor of Superior QC. And today we're going to talk a little bit about wellbore placement accuracy. And I'm going to start off with just kind of some background, some stuff that is a little bit of a repeat of what Nico said, but it helps to give you some information on where we're going to go with the rest of this presentation. So we know that when we're taking surveys downhole, we have an MWD tool, right? It consists of measurement sensors. Those are your accelerometers and magnetometers. Those sensors are reading particular aspects of the magnetic field and gravity field in order to come up with values of the magnetic field, gravity field, and the dip angle, which kind of tell you where you are as far as where you are in reference to what you're expecting to read based on some of the models that you have. So here you can see the properties that are being read by the accelerometers and magnetometers and how those calculations relate to the total magnetic field, gravity field, and dip angle. So what do we do with that information once we have it calculated? Why do we even measure those things? So we have to compare them against something. So we have what's calculated by the tool, but what does that mean? It means that we need to know what we're expecting to read for those values. So that's where the models come in. So Nico touched on it a little bit, and there's he had some good graphics to show, but these are some of the magnetic models that are available in the industry. And next to that in the table, you see some of the uncertainty associated with those. So those models are not perfect. You're never going to know exactly at that point what you should be reading for some of the reasons that Nico mentioned, that the magnetic field is always changing. And you're basically drilling underground. You're not taking direct measurements of what that field is going to be underground. So we're doing our best to model that information. And here you can see that even with IFR2, you're still going to have some uncertainty associated with those magnetic fields. And that means that when you are taking MWD surveys, you're comparing it against the values that you're pulling from these models. So you have an MWD tool, which has some uncertainty associated with the measurements you're taking, and you have a model, which has uncertainty associated with the values you're pulling from that model. So when you're taking MWD surveys, you have to know and weigh those uncertainties properly. So with that data, you get a survey, but you also get some associated ellipse of uncertainty with that. So what is that ellipse of uncertainty actually telling you? in the upper left-hand corner, you can see that there is a dot in the middle representing where your surveys say that that well is. And you have an ellipse of uncertainty, which says that your well could be anywhere in here. So that dot, I hate to break it to you, but it's not where your well is. It's your best estimate of where your well is, but the likelihood that it is there is very, very, very minimal. You hope that with your model, with your ellipse of uncertainty, that you're taking into account all of the possible wellbore locations to a certain level of accuracy. So on the bottom left, that's kind of what you're anticipating is going on downhole. So each one of those X may represent a possible wellbore location if you modeled this thing, say 1,000 times. If your model is completely accurate, you would expect to have a higher density of possible wellbore locations toward the center of your ellipse of uncertainty, which is what you're seeing there. You expect that for the most part, you're not going to be outside of it. And these are modeled to 3 sigma, so that's like a 99.7% chance that you're supposed to be inside that ellipse of uncertainty. Now, we've done some research. I know many other people have done some research that perhaps that's not always true. And you may end up with something like what you have in the upper right-hand corner here, that the errors in both your MWD surveying procedure and the models that you're using to compare them against might be larger than that. And you may be actually taking on more risk than you think you are. And if you simulate that same well 1,000 times with a more realistic expectation of your outcomes, you may see that you have a higher likelihood of kind of a spread of possible wellbore locations that don't necessarily fit what you expect. So then it becomes almost imperative that you do something about it, right? That you're doing survey corrections, a survey management procedure, because what you can do with survey management is remove some of that error. So with survey management, you're really doing 2 things. You're, number one, quantifying and removing error. So that is why on the bottom right-hand corner, that your position, your center of that cluster, the orange dot now, is moved, right? It's offset. We've taken some error and taken it out. And when we do that, your azimuth change, your inclination changes, and so your position changes. Now, the other thing that we do with survey management is we reduce uncertainty. So if we can take that error out, we can say to a higher likelihood where we actually are. So you have a decreased size of your possible cluster. So that's the goal of survey management. So when we look at survey management, the way that we like to describe it or walk through the progression of the technology is through generations. And each generation is a step change improvement upon the previous generation, right? So the way we view it, there's 4 generations on this slide. There's actually a 5th one that we won't get into, but I want to walk through each generation, what it was doing, and how the next one improved upon some of the frailties that are observed in the previous generation. So the first generation is field acceptance criteria. So that's not even a survey correction procedure. It's a way to eliminate gross error. This is what the field uses to qualify surveys. So this is what the MWD hand is doing when he accepts surveys. So basically what that is that, like I mentioned before, the MWD tool is calculating the magnetic field, gravity field, and dip angle, and it has to compare it against the reference field model. So let's say, for instance, here that you have IFR. You've pulled IFR values for this specific location, so you know what your tool should be reading. Now, you take a survey, it pumps up values that are slightly different than that. So you take what your tool is reading, you subtract off what you're expecting to read, and that difference is called a residual, right? So here we're going to take a look at a specific survey and whether or not it passes what we call field acceptance criteria. So you expect the survey to read within some tolerance of what you're expecting it to. So you have an upper and lower bounds for, in this instance, we're showing the magnetic field and the dip angle. So perfectly centered where those 2 lines cross each other would be reading exactly what the well plan expects you to, which never happens. So when a survey comes in, it's represented by that black diamond. You can see that it is outside of the red box. That red box is your basically go, no-go zone for the field. If it falls within that box, they will accept the survey, say that it is good, it is close to what we're expecting to read. Now, this one falls outside of it. So this would be a bad survey, indicated by the readings from the tool. So in the upper right-hand corner, you can say, okay, you got a good result. So there was 0.72 degrees of error in this azimuth. We caught it, and we didn't accept that survey. So what happens if we change the scenario slightly? So on this slide, we're saying that we're at 90 degrees inclination with an azimuth of 160 degrees. And the error that we caught was that there's actually drill string interference of 800 nanoteslas, which exceeds the limits that are in the error model. So we caught the proper error here. So what happens if we change the scenario slightly? We're still at 90 degrees inclination. We've only changed which direction we're drilling by 40 degrees. So you're at 120 degrees azimuth versus 160. Still the same amount of axial magnetic interference. However, when you take this survey, that black diamond is now inside the box. So the MWD hand will say, all right, this passes my check. So I will accept this as a good survey. Problem with that is you have 1.8 degrees of error in your azimuth there that you're not accounting for because you're not doing survey corrections at this point. So this is how things used to be done without survey management. So that is just highlighting what field acceptance criteria is, how it's built to detect gross error, and how it can fail. So we got a little bit smarter as an industry. We knew that was a problem. And what we did was we came to the conclusion that drill string interference was a problem, right? That we know that having ferrous components in the BHA next to a MWD tool is a problem. So what could we do about it with generation 2, which we're calling single station correction? So what we're doing with this is we're taking the magnetometer reading that is most interfered with, and we're just going to throw it out, right? So we know that it's interfered with, and we know what it should be reading because we know that from the model, we have a total magnetic field and dip angle. So we know what those values should be based on the model. And so what we can do is take that interfered with value from the magnetometer directional sensor. So in this case, we'll take this BZ reading, we'll just throw it away, and we're going to back calculate what we thought it should be based on the model. So when we do that, we're assuming the model's correct. And we're assuming the only error is axial magnetic interference. So if you assume that, you can actually introduce more error if you don't know for sure that your model is accurate or that there's no other errors that could be plaguing that sensor reading. So this was the way that we used to do it. Sometimes we still do. It's not the most accurate model, but it's an improvement over doing nothing, right? So one of the other frailties, I suppose, with that is that you do it on a survey by survey basis. You don't do it by looking at the data as a whole. You do it survey by survey, which means that the calculation that you're getting for how much axial magnetic interference is actually interfering with your survey changes every time you do that calculation. And it probably shouldn't, right? Your motor didn't change, your BHA didn't change, your components down whole should have a fairly stable amount of drill string interference impacting your surveys. So that was where we were. Now, we got a little bit smarter. We're getting better at this point. We know that drill string interference should be consistent, at least across an entire BHA run. And we know that it's not the only error source that's possible. We do have things like biases and scale factors. We have misalignments, non-orthogonalities. We have errors in our magnetic field. We know about this. So what we're going to do now is we're going to go and we're going to try and solve for more of those errors. And we're going to do it on a whole run. So that's what multi-station analysis is built to do. So one of the things that makes this difficult, makes this problem really hard to solve, is that you're doing it based on the least squares technique, which has limitations. So this is, when you break it down to what it's fundamentally doing, this is the problem we're trying to solve. We have mx equals y. So what are those things actually? So Y on the right-hand side, that's what you have, that's what you know. So that is your the residuals from your survey. So you know that you took a survey, it read one thing, you know what it should have been based on your model, you subtract them, and that's your residual. So that's what you know based on the survey data. So X in this scenario is your error terms that you're trying to solve for. So you want to get to know, you want to find out what X is, you know what Y is, and M is sort of a sensitivity matrix. It's how those things relate to each other. So how does a particular error term relate to characteristics in your residuals? So what you got to do is you got to take that matrix, the capital M, move to the other side of the equation. That is easier said than done, easy on paper, hard to do in math. So if that matrix gets too big, then you can't move it over effectively. The numerical conditioning number of that matrix is too big. And when the condition number gets too big, then it spits out basically numerical garbage, which is not reliable in calculating your actual error terms. So basically what that means is you have a limitation on how many of those error terms you can solve for. So generally speaking, you can solve for about 3 to 6, maybe 7, 8 error terms at a time, but there are more than that that could possibly be impacting a survey. So this is just a graphic showing that if you try to solve for too many error terms with multi-station analysis, you get these really large condition numbers of that matrix. It's above the limit of today's computational power. It means that you're not getting a reliable solution. You have to back down how many number of error terms you're solving for, which means you have to assume that the other ones are fine, that there is no error in those, which can be a problem. There's also some dots on there representing what the fitter solution does. So fitter is what Superior QC does. It's our version of survey corrections, and the way that we approach the math in it, it never approaches that condition number because we don't run into the inversion problem with the matrix.
So I guess along with that, then if you can reduce the number of conditional variables, then you have a more confidence in the solution.
So the problem is that the number of things that should be in this equation, M, is the same every time. But reducing it just means you're solving for less of them. And solving for less of them doesn't make them go away. There could still be there. So what you really need to do is figure out how to solve for all of them simultaneously. So that M never gets smaller.
We're only limited to being able to calculate based on basic count.
That's correct.
And you always think on top of that, the only person knows you'll learn small solving more than.
So this is multi-station analysis ability to. So let me rephrase that. So yes, the limitation is computational power. The solution is changing the way you do the math, right? So this is the least squared approach, which is what multi-station analysis uses. It's not the approach that the fault detection, isolation, and recovery algorithm uses, so we don't run into this issue. So that's basically what this slide is showing, is that we don't have this problem. So if you look at the dots on the bottom, you're looking at fitter, lateral only, full well, fitter plus rotationals, fitter plus benchmarks, fitter plus all of it. We don't approach that line. It's because we just basically started from scratch on the algorithm and made a different type of algorithm, which doesn't run into that problem.
What effect would independent outcome surveys have on that?
What's that?
What effect would independent outcome surveys have on calculations?
So not much. You still have to run them through a similar algorithm, right? If you're just talking about memory out mode type of surveys, right? So they still need to be run through a similar algorithm to clean them up, because they're still in the same environment as the static surveys. So our founder, Chad Hannock, he actually started in the industry as a multi-station analysis coder. He wrote a few flavors of it. He saw that this was a problem, And what he did about it was he invented superior QC. So the problem that we were trying to solve was that if you can only solve for 6 error terms at a time with multi-station analysis, and there are 15 possible error terms that impact the azimuth and the ISCWSA error model revisions, if you try and select 6 out of 15, there are 5,005 possible selections. So nearly impossible to get right every single time. So we're making our best estimate with the data we have, but it doesn't mean that we've gotten it right every time. So that is also a problem we're trying to solve. One more thing that plagues the multi-station analysis algorithm is that it's very difficult to drill near east-west, which has been touched on before. The reason that is because you run into a problem where your Z magnetometer reading is overwhelmingly consistent of drill string interference, more than likely in that direction, just because you're perpendicular to the actual direction of the magnetic field. It becomes very difficult to solve that term to a high degree of accuracy. So there are plenty of research papers out there saying that we should not use this approach when drilling near east-west. And our fault detection, isolation, and recovery algorithm has been built to account for all the things that I just mentioned, which were frailties in Gen 3. So now we move to Gen 4, which is the fault detection, isolation, recovery, or FITR, which is the superior QC product. So we don't have an east-west exclusion zone, and the reason that is that we take a higher level, more comprehensive look at the data. So it's not limited to a run-by-run approach. We can look at the vertical, the curve, the lateral, all together as one. So we take kind of a big data approach, data analytics, to solving for some of those error terms. And there's only one solution. So we take all of them in together at once. We're not trying to pick and choose which error terms that we solve for. We solve for all of them. So we don't run into that computational error that I mentioned before. So I will end with a short explanation as to how you can look at all the data together to solve for error terms that may be present in one section that relate to other sections. So on this graph here, what I'm showing is a magnetic field residual chart versus measured depth. So this is taking the MWD tool measurement minus what it was expected. You want that to be close to 0. And you can see that it is for 2 sections of this well. So vertical and lateral, you can see that those residuals are quite near 0. And you want them to fall within the bounds of the red line. So those are your limits. So if you're just looking at this data by itself, you say, all right, there's not much error in the vertical, not much error in the lateral. There must be something going on in the build because it exceeds the limits. But if you look at the build, what you can see, and what we do on the back end, is you can identify certain aspects of that error, which are characteristics of a particular error term. So in this instance, some of the characteristics of that indicate that there is a magnetic field strength error. So like we talked about on the first slide, even IFR has a ability to have some error in it. Mostly because you're not reading measurements downhole, you're doing your best to model it from surface. And the problem with noticing that that is a magnetic field strength error is that it would not only be present in the curve, you're reading the magnetic field in the vertical and the lateral too, right? So you would expect that it's also in the vertical and the lateral. So what does that mean? That means that there must be something that's also there in the vertical and lateral, which is causing sort of a negating effect on the error distribution residual effect here. So you have 2 errors. So you have for sure a magnetic field strength error in the vertical and lateral. You just have something else countering it, which can be tricky to solve for. But if you look at all the data as a whole and you notice that the build is what's causing the error, you can apply it in the vertical and lateral too. So that's the approach that we've taken with FITR. And it's how we use the data to more reliably provide a solution for you. Yes. So we'll apply a correction to the magnetic field in the curve and the vertical and lateral, but we'll also look at each section of the wellbore independently, because you do have errors that are only related to a run, right? So your drill string interference is not the same for the whole well. It's different for each BHA run, but things like a magnetic field error are consistent for an entire well. So it's looking at it both ways. You're looking at it run by run, and you're looking at it as the whole well also.
Also dependent too on whether or not you have the same survey.
That's absolutely true. Yes, so that's why you have to look at each run in isolation and then compare it to the results that you have for the entire well as a whole as well. That is all that I had, so I appreciate your time. And if there are any questions, fire away.
Start with the questions in Zoom.
Oh, sure. How do I get in there?
They've been asking for, they've been waiting for a minute. I can't see the mouse now.
It's on here now.
Oh, it's in there.
How do you get it over there?
Is it on the Zoom?
Yeah, right.
I think you got to get the mouse onto that screen somehow.
Yeah.
Left or right, maybe.
How do I get the mouse?
Oh, you're over there now.
I think the declination is on.
There we go. All right, let's see. Boom. All right. So.
You're gonna have to answer.
I'll read it to you. And,
Yeah, you can't really read that. It's pretty tiny.
so Mr. Shin,
One
Jim
Shin.
Shin,
Juice.
low resolution models like WMM and high resolution ones like BGGM, do they differ a lot when it comes to tracking temporal changes of total magnetic field? Is that a question for David or?
I think that was Nico's first slide, but
Then let's put that one back to the panel.
We,
Or,
we can do it, Nico, you can answer now.
yeah, sure. If you want to.
Yeah. We gotta go.
Yeah, thanks for that question, June. WMM only captures the main field. The main difference between WMM and things like BGGM would be the crustal field. So they don't change too much in sense of capturing the time variance. The big part where they differ is capturing the crustal variance and more local anomalies, which can be sizable.
And the second question came at 11:14, so I'm thinking it might be for you also, Nico.
No.
Mr. Michael Hawkins, can you describe what you think survey management transparency should look like for anyone using corrected surveys to make decisions? Accuracy of MSA and misalignment corrections or lack thereof is always a concern in my mind when anti-collision is critical.
Sure. Yeah, the data should speak to what is happening on the well, and having a transparent solution for your corrected surveys should be absolutely something that is paramount to the execution of the wellbore. So if you, I guess one way that we approach that is that there are several different reports that are made available to the operators and end users, which describe the error terms that we solve for, what their magnitudes are, what the uncertainties associated with them are, and they're all available in on a run-by-run basis and also on a entire well as a whole basis. So we don't want to be a black box operation. We absolutely want to be able to explain to you what error terms we're solving for and how they're impacting your correction size and things like that. So it's generally driven through an operator by operator procedure. Whatever information they're most comfortable with seeing is what we want to present to them. If they just want a corrected survey and nothing else, we can give that to them. If they want to understand absolutely everything we're doing, we can certainly provide that information as well.
Any questions in the room for David?
think they're picking their lunch. They're making the better choice. I got it.
Do you have a program to correct this?
Is there something incorrect about it?
No, it's just hard to make which target do we want?
Proper target error.
Thank you, David. I have to say, for someone who wasn't on the schedule to speak, you did an excellent job presenting the slides. So thank you. Our third speaker is Mr. Robert Wiley. He is the president of XN Drilling Incorporated, specializing in the development and commercialization of new technology, including drilling automation applications. He started with Gerhardt in the very early days of MWD. Robert has wide experience in global field operations, engineering, and manufacturing, and is widely known for his expertise in directional sensor technology. He has presented several technical papers on diverse drilling topics such as automated directional drilling and advanced drilling instrumentation, and actively promotes education for good practices in wellbore positioning, and he's also the treasurer of ISHWA. Thank you, Robert.
Thanks.
Oh,
You can start
Let
that.
me get it started for
Well,
you.
thanks for that introduction. I don't know who wrote it. They did a good job. I'd love to meet that person.
when you said early days, you really mean early.
Oh, I mean the early days. Yeah.
Wasn't it just WD back then?
It was just M at the time, actually. Yeah.
Just changed, just adding the show. There we go.
Boom. There you are, sir. And it'll be just the
Just the arrow keys.
yes.
Good. Thanks. Well, thanks very much for having me along, Jim, and IADD. It's one of our things at ISCWSA to try and spread the message digital year. So I'm very pleased and thankful and grateful for the opportunity to do this. What I'm planning to talk about here is just a quick introduction to the ISCWSA, for those of you who haven't been quite so aware. A bit of a summary of our more recent work, and an introduction to the online training course that we'll be offering later this year, which I think is one of our big things, and just a mention of our upcoming meeting in October. So what is the ISCWSA? Well, I stole this blatantly off of our website, and so I'm a bit of an awkward angle here to read this thing here, so I think I might try and read it off of here, which means I need some mechanical help.
A declination correction.
Yes, there we go. There we go. So yeah, as you can see, the ISCWSA was founded in the mid to late 1990s, primarily because of some of the false advertisements of what MWD companies, some of the survey companies were advertising and trying to compete. So we wanted to raise awareness and understanding of wellbore survey accuracy. We also work therefore to produce and maintain standards relating to that survey accuracy and wellbore positioning in general, and the terminology and accuracy specification to help support that and help explain what that means across the board. So one of the first things that happened was establishing a standard framework for modeling and tool performance. And that leads, of course, to the uncertainty models you've been hearing about today. What do? We typically have two parties a year. General meetings a year. Generally once in the Northern Hemisphere, North America, and one overseas, typically in Europe. The following is typically held in conjunction with the SPE annual conference. We're affiliated with the SPE as the Wellbore Positioning Technical Section. So that's sometimes where the confusion comes in, but ISCWSA and Wellbore Positioning Technical Section basically operate as one unit typically. The general meetings usually have a mix of topics. We have presentations by people who may have presented this or want to present it in a more peer-reviewed situation. So it's a place where people can have discussions up front and open about where they're going and their thoughts in wellbore placement and survey, and before they commit it to paper for eternity. We have topics of general interest to our wellbore positioning community, such as where do we think the industry is going, what's happening in different aspects of that, such as magnetics, such as instrumentation, such as the industry itself, automation, etc. And then we have updates on the subcommittee work that's been going on in between the meetings. We have several subcommittees. These subcommittee meet typically before the main meeting, and there's one work ongoing through the year to cover the topics that are of importance for the industry. Currently, we have error model management, one of the first ones, collision avoidance, education, which is a big part of our operation. Survey QC has been revised to go through some of the issues that we're seeing the last few years. Well intercept group, and finally a drilling data quality and uncertainty description group that combines input from other aspects of the drilling industry. So what we do in terms of going out from our own individual little cliques, we try and reach out as much as we can to bring other people in and involve them. There's a number of SPE papers that have been written, things like the error models, uncertainty, etc., have been published, and that's the de facto standards. We have a web presence, which I'll show you in a few minutes. We have published 2 free ebooks, which I believe are basically the industry standards on the topics. One on introduction to wellbore positioning and the other one on well interceptions. We have had a number of lecturers put on the SPE distinguished lecture tours around the world. We have another one this year. We have run 5 hits and misses workshops, which are intended for look at both anti-collision and well interception where you want to. Some webinars, topical lunches at SPE and away from there. Also, we've been involved with the API RP78 program, which is the project to put together API recommended practices for wellbore surveying. And finally, as I'll talk about later on, the certificated course in wellbore positioning. Who can join? Well, anybody can come and join us. We're very friendly, despite the way we look. We have everything from the back office staff, well planners, to field hands. We even have directional drillers in the group, strangely enough. And also, we even talk to geologists. Ed Stockhausen being a classic case, as you all know.
It is not classic.
Of course, the geodetics. So you've also got, when you're looking at placing a well, you have to know where the surface is. You have to know where you are on the surface of the earth or wherever you're drilling from. So the geodetics of the mapping aspects of that and the geomagnetics are very important for our steering operations. So our web presence is designed as our main place to go to get information about meeting updates and how to register for the meetings, where to go for historical information on meeting minutes and presentations. It's a very good searchable resource library for all aspects of what we do. And that's where you can go to look for presentations. You can search on keywords, whether it's uncertainty envelopes, whether it's data management, whether it's drilling automation, whatever you want to search on, you can go in there and look, and that will give you all the background of all the things that we've presented and published that we know about over the past 20 odd years. Also, the subcommittees do their work through there. Some of the subcommittee pages are restricted to the subcommittees themselves because they're working groups, but you're welcome to be in touch with them and join. And also, the links are on there for any contacts for the committee and other people in the group. And here are a couple of the links of importance. We've got up in the top left-hand corner there, a link to join and a link to be added to the email distribution list. These days with data privacy, we have to follow the regulations globally in terms of sending out updates. So that's why we ask people to join and register on the website so that you will get those meeting updates on a regular basis. Further down, you can see also the links for SPE and the LinkedIn group we have there. So looking forward, where we are today, our next general meeting is going to be in October. We had planned to hold that in person in Dubai with the SPE ATCE, but given the current circumstances being extended, we're decided to go virtual with that. And it will be in the mornings of October the 6th and 7th, mornings Houston time, from about 8 o'clock to 11:30. And we've had the last two meetings have been totally virtual, so we're getting used to doing that now. The call for papers is open, and there's a link for submission on the website. So if anybody's interested in presenting to that, please go click on that link and send in your abstract. We're particularly interested, or I'm particularly interested in papers around energy transition and climate change these days, and we're to see where that's going, how that's going to affect our industry. What are we going to do? For example, some of the geothermal wells are looking at multiple parallel well bores or intercepting well bores. Some of the other aspects are maybe drilling into mines and things like that. So there's a few aspects of what do we do as a industry to help support that, and where do we need to go for our wellbore positioning aspects. The education subcommittee is one of the more active groups in terms of the outreach, and they are leading Mahmoud El-Kadi, or Mahmoud is Gizawi, sorry, is leading that group, and he is going to be leading a special session at the SPE ATCE in Dubai on a more wider reach aspects of well positioning in terms of all the aspects of how do we drive the value. People look at surveying as costing more, but really you're looking at how does that impact the overall asset value. Good well positioning practices can reduce your drilling costs because of less tortuous wells. You're going to have maybe less frac hits and better resources coming back from your reservoir down the road. So we're trying to bring a lot of people in there from both the subsurface areas and the drilling areas together. The education subcommittee are also putting the free ebooks on a site called Manuala, I think I spelled that wrong, manula.com, as searchable PDFs for ease of use, and working to prepare the ISCWSA certificated course on introduction wellbore positioning. The API RP78 progress is continuing. The chapters have been mostly rewritten to combine them better. The next steps are to combine the chapters together with an overall technical editor to make sure everything relates well, followed by a technical writing to make sure the style is appropriate and consistent throughout the book, or throughout the procedures. And then that will be sent out for wider reviews and comments before it is published. And again, membership sign up is very important. So please go ahead and to the links in the web page and sign up so that you can get up-to-date information on a regular basis. The Well Intercept Subcommittee has been quite busy. They've got a distinguished lecturer coming up for the coming season on good practices in well control intervention, particularly with relief well intersections involved. They've also released the latest version of the free ebook on well intercepts. It's very clearly titled, very creatively titled Well Intercept Subcommittee ebook, so easy to find. And there are some of the topics that they've looked at on there. The online training course is the big thing we've got going on today, or these days. This course was previously developed and run by the University of Highlands and Islands in Scotland with Professor Angus Jameson, who one or two of you may have come across in your careers. They found that that's not longer part of their curriculum, so they agreed to let us take over all the materials, all the course. So we're in the process of converting all that course to run under modern learning management system for online course. These are often known as MOOCs, massive open online courses. Ours is a small private online course, which is a SPOC, so maybe appropriate for drilling in Mars as well. Thank you. So the way the learning management system works, we're using the OpenEDX system, and it will be delivered through the ISCWSA website. We're linked entirely integrated with that. Angus Jameson is still the main lecturer on this, and we have lined up a training company run by him to do the final examinations at the end of the day that will award the certificate. The course itself was initially a series of long lectures, some of them an hour to hour and a half, were broken up into modern techniques of shorter video lectures, interspersed with readings, problems, exercises, and simulation examples. But the course forms a similar outline as before. As you can see on the right, it starts out with a session on mapping and geodesy, a session on Earth's magnetic field and interactions, a session on basic drilling rigs, well planning and directional drilling, the BHA design. The BHA design section, I found that fascinating myself, and it exposed some of the things that I didn't realize I didn't know. It was very interesting. Data management, quality control, and depth management are other section as well there. And I think that relates to some of the stuff that was asked in the last session there about what do we do about auditing survey corrections. You know, that's very appropriate. Your whole data management structure has to be in there. We go through basic survey tool types, going through from acid bottles, which I'm sure Jim remembers very well, to some modern tools, and even past the inertial gyro tools, inertial tools. We go through survey uncertainty and how those ellipses of uncertainty are determined and how you get there, collision avoidance, and then high accuracy drilling with the different techniques for applying these survey corrections, and one of that kind of thing. We're planning to offer this starting probably about September with our initial group going through there. And we're going to be looking for applications to register for the course through ISCWSA website here pretty soon. Please let me know if you're interested. We've had a couple of companies that have committed already to either put their entire staff through it or a significant number of their new engineers and existing engineers, geologists, etc. through that. To get the certificate, students will have to pass the final exam. So in the course, we talked about basically the goal of this course is that you'll be aware of how to plan a good survey program, which goes everything from selecting the appropriate tools for the job through your survey management techniques and where the money might be spent or where you might not want to waste money or you don't have to spend money on the latest survey super tool in certain circumstances. How do you spend it appropriately? How to do the high accuracy drilling, basic well planning, basic directional skills, and then how to apply all those corrections. So that even if you're a geologist and not applying them, you should know about what they are, how to apply them to make sure they're being done appropriately for your aspect of the job. I won't go through this in detail, but it's the same list of course content basically that the UHI had. It's quite extensive, going from survey calculations, from basic surface location identifications, like mapping, through the measurement of Earth's field, where you are in relation to that, whether it's magnetic or gyro, then going to the well planning, how to land, land in the appropriate part of the reservoir, etc. As an example, here's one example of one of the units. Each of the course is broken down to sections and then subsections below that. And some of the units will include things like videos. You'll be able to go through the navigation of these things very easily. For example, you'll see on the right-hand side of the video there's a transcript, which means that instead of having to try and scroll along the bottom with a scroll bar, you can just go click on the word in the transcript that you want to go back and review or look at again. So it makes the navigation very easy. The navigation through the course is very easy by going through the section at the top. Each of the sections is named and numbered, so you can identify where you are very quickly and easily in the course. So it's easy to go through from there.
Is that a halo?
So I think, yeah. So the question from the audience for those on Zoom was, is that a halo over Angus's head? And I think that's one of these artifacts of brilliance, So anyway, so there's the intention of this is good modern learning techniques, progress tracking, the ability to interact, the student to interact with the other students as well, and practical exercises that are actually going to be useful for whatever job you're doing. So that's a quick summary there. And it looks like the slides are coming out. So Jim, do you want to hold questions till later, or you want to?
I got a quick question for you. So is that course all pre-recorded videos, or are there some live sessions on Zoom or whatever?
Sure. So the question from the audience here was, is this all pre-recorded videos, or is there some live interaction and things like that? Most of the material is pre-recorded, but it is direct interaction. So the videos themselves are recorded so that you can go through them online from where you're at. The exercises themselves, some of the exercises will then be answered online and interacting online. But the intention is to have, there's discussion sessions in there as well, where you can post a question or a comment on different aspects of the topics. And then we are planning to have tutorial sessions that go along with this, just like there were in the previous version of the course. Of course, how much we're going to charge. So UHI price was $3,000 per student. We're looking to come in a bit lower than that. So we're targeting at the moment $1,000 a student, including examinations and things like that. The initial running of the course will offer a discount. So later this year, for the first people that go through it, they'll get a discount on that. And we hope to maintain that pricing, but time will tell whether that's something we can substantiate to maintain the quality and go forward at that price or not.
Is there like a target audience in terms of how much knowledge there already is?
Sure, absolutely. So the question is there a target audience in terms of past experience and knowledge of surveys, etc.? And the target audience is basically anyone who uses the well positioning data in their job. And that can go from anybody from directional driller, MWD survey corrections, geomagnetics, subsurface geologists, production people who want to know where their wells are. There's no prerequisite knowledge required for the course. This is an introduction to wellbore positioning. It's a widespread introduction to wellbore positioning and gets you very far up the learning chain. But it's something that I would expect all the survey management companies to have de facto. And most MWD companies should have several people at least involved in that. So it would be good for an MWD engineer to have this training. Some companies have told me, a couple of operators have told me they may expect their suppliers to have this certificate going down the road.
All right, thanks, Robert.
Well, thanks very much. Thanks again for having me.
We're going to take a few minutes break for lunch, and then we'll come back and we'll have our panel questions.
Okay, for those that are on Zoom, we're going to go ahead and end the session. I appreciate all the questions and everything that came back and for your participation.